All right, so this is, I think, lecture 23 of Math313 number theory. So what we're going to do is we're going to continue our study of Diophantine equations. So there's two choices. We can do the Hensel-Lemma stuff first, or we can do the Fermat's last theorem. And I think based on what we did yesterday, it makes more sense to start with Fermat's last theorem and then pivot to Hensel's lemma and some strange things called the p-adics. This is not a class where we will get into too much of the p-adics, but we will at least let you know that they exist and let you know that strange things can happen. Okay. So Fermat's last theorem. X to the n plus y to the n equals z to the n has no solutions in the integers if x, y, z does not equal 0 and n is greater than or equal to 3. If n equals 2, this is just the Pythagorean theorem, and we know what's going on. You can't sit there. It's going to completely throw me off the whole day. Yeah, can you move? Thank you. So if we put x, y, z non-zero and n equals 2, this is the Pythagorean equation. We did that last time. We know how to handle that. So Fermat claimed he had a proof. It may be a real simple proof, but the margin didn't have sufficient space. All right. The final proof by Andrew Wiles needs significantly long margins. It's well over 100 pages, building a lot of extremely advanced math of the 20th century. It's commonly referred to as proof by Wiles with an assist by Taylor-Wiles. There was a gap that was found in his original attempt. Even if that gap had never been fixed, he still would have proven a major result on the way. And then he eventually brought in a former grad student of his, Taylor, to help him fill that last gap. Based on how much time we have left in the semester and the fact that you have not taken too many graduate classes in Galois cohomology and stuff like that, we will not do the general case. We will concentrate instead on specific values of n. And so it turns out that there are certain values of n that are easier to understand than others. And to some extent, if you can understand some values of n, you can understand others. So for instance, let's say we know no solutions if n equals 4. What else can you tell me if you know that there are no solutions when n equals 4?
No solutions, n equals 8.
Or? So any multiple of 4, because now you could just do x to the m to the 4th plus y to the m to the 4th equals z to the m to the 4th. So this tells you it's almost sufficient to study this for prime powers. I'm sorry, for primes. Because if we can just show that there's no solution for every prime m, we're done. There's one thing we have to be careful about. It's not enough to just do it for every prime p. So I would love to say, if we know that there's no solutions for every prime p, there's no solutions in general, because I can just get to anything by multiplying. What's the one number I have to be careful about? Yes?
2, because we know 2 has solutions.
We know 2 has a solution. If p equals 2, there are solutions to x squared plus y squared equals z squared. So the problem is if something is a multiple of 2, crap. Well, there's only one multiple of 2 that's bad. What's the only multiple of 2 that's bad? 4. Anything else, if I give you something like 6, then 6 is going to have a it's going to have a factor that's not 2. It's going to have a factor that's 3. If I give you 21, it'll have a factor p equals 7. So the only thing I have to worry about is 4. You might say, well, what about 8? Well, if I have 8, I could say if there's no solutions with 4, then there'll be no solutions with 8, because I could do x squared to the 4th plus y squared to the 4th equals z squared to the 4th. So if I can show that there's no solutions for primes, so show no solution if prime p greater than or equal to 3 or 4. And then we have Fermat's last theorem. It turns out certain primes are very easy to analyze. They're called Sophie-Germain primes. And so these primes are such that p and p minus 1 over 2 are both prime. 2 is sometimes a troublesome prime. It's small. Let's assume our prime is big, like 3 or more. Okay? Could p minus 1 ever be prime if our prime is big like 3?
No.
P minus 1, not p minus 1 over 2, p minus 1. Could p minus 1 ever be prime if our prime is big like 3? What's 3 minus 1? 2, right? 3 is not sufficiently large. But if if the prime is really large, like 5, then we know p minus 1 can't be prime. So once our prime is sufficiently large, p minus 1 will never be prime. So if I want to ask for primes such that p and p minus 1 are both prime, this is really boring. The only option is p equals 3. So instead, it turns out we look at numbers where p and p minus 1 over 2 are both prime. And in that case, we know p minus 1 is going to be even, because p is large, it's at least 5, so it's an odd prime. It has to be a multiple of 2. And then if that's the only thing that divides it, if that's also prime, it turns out FermatLastThm can be attacked in a situation like that without too much trouble. And so you can prove FermatLastThm for Sophie-Germain primes. Unfortunately, not all primes are Sophie-Germain primes. So if we take 7, 7 minus 1 is 6 divided by 2 is 3. So 7, 3 would be a Sophie-Germain pair. If we take 11, 11 minus 1 is 10 divided by 2 is, oh, maybe every prime is Sophie-Germain, right? This is beginning to look good. What about 13? Yeah, 13. So the pattern feels very fast. With 13, we get 6. And 6 is not prime. So unfortunately, most primes are not going to be a Sophie-Germain prime pair. But that is one way people attack things like FermatLastThm, is they try to look for special primes. What we will concentrate on today is we will concentrate on the case n equals 4. Okay? So we're going to study n equals 4. And we're going to do a little bit more. We're going to look at x to the 4th plus y to the 4th equals z squared. And we're going to show that there's no solutions. So this is actually a little bit more powerful than FermatLastThm. FermatLastThm said that this should be a 4th power here. We're only doing it a square here. If we can show that there are no solutions to this, it's not so hard to show that there's no solutions to that. Because we can always write, if we want to solve, a to the 4th plus b to the 4th equals c to the 4th, I can write that as c squared squared. So if we can show that there's no solutions here, then there's no solutions to FermatLastThm with n equals 4. Okay. So the question is, how do we prove this? So the method is one of the most powerful methods in mathematics. It's called the method of descent. And we've actually seen the method of descent in this class. You show that the set of solutions has a nice property, that you can associate a value to each one, that you can order them by size. So the word we often use in the book is we order the solutions by their height. And that there are only finitely many solutions with height above a certain point, with height at most a certain value. And if there's only finitely many, there's got to be one with the smallest height, or maybe several with the smallest height. And what you show is that if there is a solution, you can always find a solution with smaller height. Therefore, you can find infinitely many solutions, and that contradicts the fact that there should only be finitely many solutions of a given height. Where have we seen this idea before?
Proving that
Yeah. When we wrote root 2 equals a over b, we assumed we had a solution with a and b non-zero integers, and we chose them to be relatively prime, and we took the smallest b that worked. And then we showed if this was true, we could find a new rational solution that had smaller b. And since the smallest value of b is 1, we're not going to have a ratio of 2 integers where b is less than 1. We're not allowed to divide by 0 here, because we have a guest today, otherwise, sure. we can't have b getting arbitrarily small. But we showed that if there was a rational solution, we could find a new solution with smaller b. And then we just apply lather, rinse, repeat. We then apply that here, and we get another one that's small, another one that's small, another one that's small, and we would get this infinite chain descending. And so if a rational solution exists, infinitely many solutions exist that are distinct. Contradiction. So we're going to do the same thing over here. We're going to assume a solution exists. And then from the existence of one of these solutions, we're going to then show that there exists a new solution that's smaller. So we'll assume we have a smallest solution, and then we'll find a smaller. Okay. What sweatshirt am I wearing today? What school?
Ohio State.
Try again.
The
Well, actually, you're close.
University.
The Ohio State University. Right? This is not a Ohio State University. This is the Ohio State University. Okay? When I say you take the smallest solution, when I say the smallest solution, that implies that there is one solution that's smaller than all others. We could have an extended nomenclature. Maybe we can assume, since everything is even, that all of our numbers are non-negative. And we will order them, and if we want to compare two solutions, whichever solution has smallest value of z will be considered the smallest. If two have the same value of z, how do we determine which one is the smallest? Smallest y. And if they have the same value of y, then they have the same value of x, and there would be this. So we could maybe assume x is greater than or equal to y, and then choose the smallest z, and then if we have two things with the smallest z, we could put in some kind of nomenclature like this to order the solutions and get a unique smallest solution. There's really no need. It's going to suffice to take a solution where the value of z is as small as possible over the whole set of solutions. Okay? All right. Does this equation look like any equations we've studied? Yes. It looks like the Pythagorean theorem, right? Which is one of the reasons why we did the Pythagorean theorem on Wednesday. So we can write this as x squared squared plus y squared squared equals z squared. So I will be glancing at my notes so that I use the same letters of the alphabet as the book does, and just to try to keep things consistent. It doesn't really matter, but what should we be able to conclude right now from what we did on Wednesday? And you're welcome to answer this because you've also covered that now. What do we know?
We know that we can write x, y, and z as M&M.
Almost. Not x, y, and z. Close.
Oh, x squared.
X squared. So we now have a Pythagorean triple, right? We just parametrized the Pythagorean triples. And so I want to use the book's notation. And then this way, if there's any mistakes in the book, we can alert the author. So we can write x squared as 2st, y squared as s squared minus t squared, and then z as s squared plus t squared. So this is because of the work we did last time. Okay. What should we do now? If we substitute in, it all checks, the algebra works. There's something else we can do now. One of these three is better to look at than the others. Which one should we look at? Yes?
Y squared, because we can factor it.
We could factor it, but I think there's something better to do with y squared than factoring it. And this is where I'll give you a small hint. How you represent things affects how you look at things. Yes?
S squared is equal to y squared plus t squared.
Yeah, we could write this as y squared plus t squared is s squared. What should you think of as soon as you see y squared plus t squared is s squared? Pythagorean theorem again. We have a formula for Pythagorean triples. This is another Pythagorean triple. I think they want to use the letters A and B. So they want to use t equals 2ab, y equals a squared minus b squared, and z is a squared plus b squared.
That should be S, not Z.
That should be, thank you, that should be S, not Z. I just hate writing S so much. All right, so now we have a formula for x in terms of S and t. And then we can then write x in terms of a and b. Right? So x squared is going to be 2st. So t is 2ab, s is a squared plus b squared. So please make sure I'm not making too many algebra mistakes. We'll get 4ab a squared plus b squared. My feeling is just when we have this many equations on the board, let's just write it nicely as to what's going on. Y is equal to a squared minus b squared. Okay, nothing I really need to do over there. Y is equal to a squared minus b squared. And then z is s squared plus t squared. So s squared is going to be a squared plus 2a squared b squared plus b squared. And then t squared, all right, well, I'll just leave it like this and hope that I don't have to do too much with z for now. So for a squared b squared. Okay. So here's everything now in terms of a and b. And the goal is we want to find a new formula, 3 quantities, such that the 4th power of 1 plus the 4th power of the 2nd equals the square of the 3rd. What can you tell me about this number over here? What kind of number is 4ab a squared plus b squared? It's an integer, but it's a very special type of integer. What are the possible values for that integer? Could the integer equal 3? It's even. It's multiple of 4. Okay. Could it be 7? Okay. Could it be 12? So look at the whole.
That has to be a multiple of 8 too, doesn't it?
I'm sorry?
That has to be a multiple of 8.
Why does it have to be a multiple of 8?
Because if either A or B is even, then that becomes
Good. If either A or B is even, we're going to get another factor of 2 here. If they're both odd, we'll get a factor of 2. So it's got to be at least a multiple of 8. Okay, fine. Is it possible that this could equal 8? Look at the whole thing. What do we know 4ab a squared plus b squared equals? It's a square. Right? This is a square. It can't be 8. Could it be 16? Possibly. 16 is a square. Could it be 32? No. We know 4ab a squared plus b squared is a square. Because we know it equals x squared. This is all, the whole point of today's lecture is to keep looking at the right parts of the board. Did I tell you about my 2 friends who quit college for a year to help the amazing James Randi? He is a magician who debunks people who claim to have psychic powers. And so I got to see some of his tricks as to how to get people to look at the wrong thing. Fascinating what you can do. So here, the whole point is looking at the right part of all the algebra and seeing what's going on. And remembering, what is the goal? The goal is we start off with a solution to this to the 4th plus this to the 4th is that to the 4th. And we want to find a new solution. Probably going to involve A's and B's, maybe even more letters. Fortunately, we have a large alphabet. In an emergency, what alphabet could we go to? Russian? I mean, we could go to the Russian alphabet, but I would much rather go to the Greek alphabet as a mathematician. But if necessary, we could go to the Russian. I can go to the Hebrew alphabet. Russian alphabet is fine. Egyptian hieroglyphs. We could also go to emojis. right? Doesn't really matter what we use. So I'm going to write, how should I write 4? 2 squared. And now I know this whole thing has to be squares. Do A and B have any elements in common? So, do A and B have any elements in common? Imagine something divides A and B. Then it divides T. Does it divide Y? Yeah. Does it divide Z? Yeah, if something divides both A and B, it divides the squares and it divides this. So if something divides A and B, it's going to divide X, Y, and Z. That means our solution is not minimal. We have to be careful because we have X to the 4th power, Y to the 4th power, and Z squared. So if it divides X once, how many times must it divide Z for me to pull it out? So for instance, let's say 3 divides X and 3 divides Y. Then I get 3 to the 4th divides the left-hand side. How many 3's must divide Z? 2. But what's nice here is we have A squared, B squared, A squared, B squared. So if something divides both A and B, its squared divides A squared, its squared divides B squared, its squared divides A squared times B squared. So if A and B are not relatively prime, we have a new smaller solution. So we can say, without loss of generality, there does not exist a prime that divides A and B, as we would then get P divides X, P divides Y, P squared divides Z. Original is non-minimal. So because our original solution is minimal, there can't be a prime that divides both A and B. Okay. The goal is to hopefully show that maybe A is a square, B is a square, and A squared plus B squared is a square. So we know A and B have nothing in common. Can A and A squared plus B squared have anything in common? So what would be the GCD, the greatest common divisor of A and A squared plus B squared? This is the same as the GCD of what? A and B squared, because clearly anything that divides A squared. So this is just the same as the GCD, the greatest common divisor of A and B squared. But we just assumed that A and B are relatively prime. So A shares no factors with B, B shares no factors with A, and neither one of them shares any factors with A squared plus B squared. So we can now say the GCD of A and B equals 1. Okay. So now that we know A, B, and A squared plus B squared have no factors in common, what can you tell me now about the numbers A and B? They're perfect squares. By the fundamental theorem of arithmetic, we can write A and B as a product of primes and prime powers. If a prime divides A, that prime can't occur in B and it can't occur in A squared plus B squared. I have to have a perfect square. That means all of my prime powers must be even. And the only way if a prime divides A that I'm going to get powers of it is from A. So A and B have to be perfect squares. What letters should we use now? I forget what they're using now. Yeah, it's not the letters I would have chosen. But it's not a bad choice, and I can understand why they would make this choice. So they're going to choose capital X and capital Y. Right? Is it not turning? Just making sure this is good. Okay, so what we can do is, I think they want capital X, so we want to write A as capital X squared and B as capital Y squared. So for those of you who have taken probability with me, you're used to me writing like this. The point is I want to make sure I do not accidentally confuse a capital X with a lowercase x. In a textbook, it's very different than doing things on a blackboard. So we now know if A is x squared, B is y squared. All right, so we now get x squared is 2 squared x squared y squared x squared plus y squared. Y is going to be, what's y going to be? X to the 4th minus y to the fourth?
Wouldn't that also be x to the fourth plus y to the fourth and the other?
Oh yeah, I was going to say this should be x to the fourth plus y to the fourth. Thank you. Y will be x to the fourth minus y to the fourth, and then z will be x to the fourth plus y to the fourth to the fourth. No, squared, sorry, squared, plus 4 x to the fourth y to the fourth. Okay, a lot of stuff on the board. Yes?
We know that x to the fourth plus y to the fourth has to be a perfect square.
Excellent. Why does that have to be a perfect square?
Because x squared, we already determined that a squared plus b squared would be a perfect square.
Okay.
And that's
So this is a perfect square. This is a perfect square here. This clearly has to divide x squared. And so now we get x to the fourth plus y to the fourth is some number squared. Do we actually need what y is over here, or z? No. Thank God. Because those expressions are getting quite involved. All that matters here is x to the fourth plus y to the fourth has to be a perfect square. And so we now have a new solution. So what I'm going to do is I'm going to come back over here. So we assumed we had a solution. And now we have a new solution. Big X to the fourth plus big Y to the fourth. What do you think we should call it? Big Z to the fourth. Or actually big Z squared. We're almost done. Yes?
since we know that x is less than or equal to z, and also that big Z is equal to x over 2 big X big Y.
Right.
And so that means big Z is less than x, which is less than or equal to small z, so big Z is less than normal z, which...
Right. So basically we just need to chase things, and the goal now is to show x to the fourth plus y to the fourth big is less than or equal to, I'm sorry, strictly less than x squared plus y squared. Because if we can show that this sum is less than this sum, we found a solution that's smaller. So now it's just going through the algebra and piecing things together. So this is a way to prove Fermat's last theorem in the special case n equals 4. Right. The idea of this method of descent is really nice. And this works for certain exponents. I think there's a nice way to do this also for cubes. But in general, we need other techniques. But this idea of having some kind of solution space, we only have a bounded number of a given value or lower. And showing that if a solution exists, you can get this infinite chain going down. It's an extremely powerful idea. So we just need to show that x squared plus y squared with bigs is smaller than x squared plus y squared. All right, so how should we do this? So it's just now a matter of collecting the algebra. So little x squared would be this, little y squared we would be squaring this. So we could start, calculating all these things together. So x squared plus y squared is going to be 4ab a squared plus b squared. And then plus y squared is going to be plus a squared minus b squared squared. Okay. But now we know x to the fourth plus y to the fourth. That was just a squared plus b squared, right? This part over here, this is just x to the fourth plus y to the fourth, right? So clearly, 4ab is greater than or equal to 1. This over here, best case for us is at 0 because we're squaring it. So this is clearly going to be strictly greater than x to the fourth plus y to the fourth. Because the thing we care about was just a subset, a subterm of this. So x squared plus y squared, Oh, but that's x squared. Okay. But we want x to the fourth plus y to the fourth. And this is x squared plus y squared.
So we just square it.
Well, which is larger, x to the fourth or x squared? X to the fourth. Unless they're both 1, in which case they're the same. But this will be, we can clearly get x to the fourth plus y to the fourth is greater than or equal to. If x and y are both 1, it's a strict equal. If either one of these is greater than 1, I'd much rather raise a number to the fourth power than the second power. So we get a nice chain like this, yes?
Do you maybe actually need the to the fourth power? Because what if, I don't know if we accounted for this, but what if a is positive and b is negative? And then we have 4ab.
Ah.
And it was something smaller.
Okay, good. So we do have to worry about that.
But if you're taking x to the fourth plus y to the fourth, you're squaring all those terms, so that
Right.
you wouldn't have to worry about negatives.
We don't have to worry about that. You are absolutely correct that we need to be aware of it, but it can't happen in our case. Why can't it happen in our case?
Because a is already x squared.
I'm sorry? Because a and b are both positive. So you're absolutely correct that we need b is greater than or equal to 0. But fortunately, we have that. Yes?
Stops us from just looking at the last thing we wrote down and saying x to the fourth plus y to the fourth is less than or equal to x squared.
We probably could have done that as well. And so we could have had x to the fourth plus y to the fourth is less than or equal to x squared, so it's less than or equal to x to the fourth, so it's less than or equal to x to the fourth plus y to the fourth. That would work. That would work as well. There's lots of change through the algebra. I was trying to write exactly what we have, but that would be, I think, a faster way of doing it. So this finishes the proof by descent. We now have a smaller value for our z component. And so you give me a solution that works, you give me a triple, and I can come up with a new triple with smaller value of z. Well, z is a positive integer. I can't do this infinitely many times. But if there's a solution, I can always just lather, rinse, repeat, keep doing it. Contradiction. So there's no solution to Fermat's last theorem when n equals 4. So it's a very nice result. Okay. And what I like is we used very critically the analysis we had for Pythagoras. So that wasn't just a cookbook problem. That wasn't just something to fill up a day's lecture. That was the key ingredient in that we were able to parameterize these solutions. So in general, the first thing you want to do whenever you get something in mathematics is ask, does it exist? Is there an object? Is it worth searching for it? The next question you might want to ask is, how many are there? And the next question you might want to ask is, where are they? So a lot of times we have existence proofs that a solution exists, but we don't necessarily know that a optimal solution exists. For those of you following the United Airlines, a solution exists, but knowing that solution exists was not enough to help United. They needed to find a better solution than the one they did. So the next part of today's lecture is trying to switch to finding solutions. And so in the last class, we looked at what happens when we study some equations modulo primes. And we saw that when we looked at things modulo primes, we could sometimes use this to prove things can't have solutions. So recall maybe 2x plus 4y equals 1701, where x and y are integers. There's no solutions. No solutions as no solutions to x plus y is congruent to 0. I'm sorry, it's congruent to 1701 mod 2. So by looking at this equation mod 2, we can immediately deduce that there's no solution. So the question becomes, what happens if it does have a solution? What happens if it has a solution for every prime? Or maybe every prime and every prime power? Is it enough to do something like that and then piece things together? And so I gave you, two equations last time that have solutions mod p for every prime, but don't have solutions over the integers. This is quite upsetting. We'd love to be able to solve these local problems and piece them together. This should remind you of some very bad numbers that are closely related to primes. Remember which? The Carmichael numbers. So we have Fermat's little theorem. I mean, this is the Fermat day. So we have Fermat's little theorem that if A and P are relatively prime, then A to the P minus 1 is congruent to 1 mod P. So if you have A to the n minus 1 is not congruent to 1 mod n, that implies n is composite. And what's wonderful about this is you know n is composite without even having to factor n or find a number that divides n. Unfortunately, there are numbers n that pass this test for every a relatively prime to n, but are not prime. And these are the Carmichael numbers, and they actually cause a lot of problems in cryptography. Fortunately, there are very few Carmichael numbers relative to prime numbers. So if you have a number that passes all the tests, odds are it's prime. And you'll sometimes even hear the phrase an industrial prime. You know, we're not positive it's prime, but it's passed so many tests, we're reasonably confident it's prime because there are so few things that are not prime that will pass this many tests, we'll just act as if it's prime. If you need to be damn sure, let's say you're dealing with national security, you probably want something a little bit stronger than industrial prime, and you'll do the more involved test to make sure it's actually prime. So we could study this mod 2, and we could see that there's no solution mod 2, so there can't be any solutions over the integers. Let's do another one. Let's say we're trying to write n as a sum of two squares. We gave a heuristic last time that infinitely many n won't work. And we said, well, look, x and y are clearly at most square root of n. The number of pairs you have is roughly root n choose 2, which is going to be roughly of size n halves. So at least 50% of numbers are not going to work. I'll give you another argument now that will show at least 25% of numbers don't work. So it's not as strong of a result, but it's another nice technique. In all of these things, you want to decide what you want to look at things modulo. And we're going to look at this mod 4. So when I look at numbers squared, mod 4, 0 squared is what mod 4? 0. What's 1 squared mod 4? 1. What's 2 squared mod 4? 0. What's 3 squared mod 4? 9. So x squared is either 0 or 1 mod 4. Y squared is 0 or 1 mod 4. So when you look at the possible values for x squared plus y squared mod 4, we could have 0 plus 0 is 0. We could have 0 plus 1 is 1. We could have 1 plus 0 is 1. We could have 1 plus 1 is 2. Which values of n will not have solutions? Yeah, if n is 3 mod 4, so no solution if n is 3 mod 4. So the argument I gave you last time showed 50% of numbers roughly don't work. This shows only 25% of the numbers don't work. But it's a nice technique. It's a nice complement. That when I look at this equation mod 4, we can see that numbers of this form clearly can't work. So there were two approaches. So the book goes through some calculations where they take some equations, they try to solve it in mod a bunch of different primes, and then they use the Chinese remainder theorem to try to combine those solutions for all the different primes to one solution. That's one approach. Think of this as the breadth approach. You're looking at all the primes, you're treating all the primes equally, you're trying to look at all of them and combine them together. The other approach is the depth approach, is fix one prime and study it really well for that prime. Well, you can't really study it that well for one prime, that's just one equation. So what you do is you study it modulo that prime squared, that prime cubed, that prime to the fourth. And the idea is that if you can study it for all powers of that one prime, you can then somehow build this up to whether or not the original thing has a solution. So this is similar to Taylor series. And it's similar to something you might have seen in differential equations. Differential equations is the class that I think most people typically do not take. So out of curiosity, how many people here have taken differential equations? Oh, excellent. This is more than normal. So think series expansions. So when you're trying to solve something in differential equations, you'll often assume, y of x is the sum of, an x to the n. Y prime of x would be the sum of n, an x to the n minus 1, et cetera, for however many derivatives you have. You would then shove it all together, and you would get some kind of relations for the undetermined a's, and you try to solve them iteratively. We're going to try to do the same game here. But instead of solving it in terms of the sum of y is an x to the n, instead of our Taylor series, the Taylor series of f is the sum of the nth derivative at 0, x to the n over n factorial. These are series expansions you've seen before. We're going to do a p-series. We're going to try to write our number n as a0 plus a1p plus a2p squared plus a3p cubed. And we're going to try to expand our number in powers of p. What's a little problematic about writing a series expansion like this? Yeah.
If the a's don't go to 0, it becomes infinity.
Yeah, if the a's don't go to 0, it becomes infinity. That's a problem. And you should think of this as almost writing your number base p. And so the a should be between 0 and p minus 1. Or you're looking at things mod z mod pz. All right, so the fact that the number could be plus infinity is a bit of a problem. So I'm not going to go into too much detail here, but this would be done, I believe, in an algebraic number theory class. You introduce a size of the different term. And the size of your number is going to be related to the power of the prime that divides it. And the larger that power is, the smaller the number. So we might decide that this has length 1 over p, this has length 1 over p squared, this has length 1 over p cubed, 1 over p to the 4th. So the higher and higher powers are making things smaller and smaller and smaller. And that you can actually make sense and talk about this number converging. This convergence is called p-adically. You've actually seen something like this. What's 1 plus 2 plus 4 plus 8 plus 16? What does this equal? Yeah. You pretend you're in an econ class or a physics class. What would this equal? No. In a math class it would be infinity, but if you're in like econ or physics. Not 2 to the infinity. What does this look like on the left? What kind of series is this? Geometric. What's the ratio? 2. So this should just equal 1 over 1 minus 2, which is negative 1. Right? So the sum of all the powers of 2, it overshoots infinity, comes in from the negative infinity, and almost makes it back to 0. Does this make sense?
Kind of makes sense because you just say like, because it's always going to be 2 to the n minus 1. So you're
Well,
just going to say, we already did that.
well, let's call this number x. What's 1 plus x? Well, that'll be 2 plus 2 plus 4 plus 8 plus 16. What's 2 plus 2? 4 plus 4 plus 8 plus 16. 4 plus 4 is 8. So you get 8 plus 8 plus 16. 8 plus 8 is 16. It just pushes it all the way off to infinity. So this number really does look like negative 1.
But it's not.
P-adically it is. The p-adics are strange. Yes?
Is this also where like 1 plus 2 plus 3 plus 4 is
Yes. But that's not p-adically, but yes. So if you sum all the positive, I mean, this is a little bit strange. It's a good thing to end on. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 equals negative 1/12.
If this is true, I'm dropping the major.
All right. I'll put it in quotes. How's that? Will I keep you in the major with quotes?
This was actually I thought it was just like the integers, not the.
Oh, I'm sorry. Yes, I'm sorry. Sorry. Yeah, no. Sorry. Yes, it's 1 plus 2 plus 3 plus 4 plus 5. So if you sum all the integers, you get negative 1/12. If you sum all the powers of 2, you get negative 1. Does that make any sense? So all the powers of 2 are a subset over here that gives me negative 1. And then the rest of the stuff, I guess, is a little bit of positive. It moves me from negative 1 to negative 1/12. So this is coming from the Riemann zeta function. What's going on is you're trying to interpret a series, an infinite series, in a place where it's originally not defined. So if you look at the geometric series, 1 plus x squared plus x cubed plus ... This equals 1 over 1 minus x if the absolute value of x is less than 1. However, if I look on the right-hand side, does this make sense if x equals 2? Yes, this right-hand side is well-defined so long as x is not 1. For any other value of x, this right-hand side is well-defined. This left-hand side, not even close. So what we can say is we will continue, we will analytically continue, we will extend, and by this infinite sum, we really mean this function 1 over 1 minus x. How many of you remember the financial collapse around 2008, 2009? Yeah. So what happened is they used some math formulas in places where they had no right to use them. And oh yeah, these things are independent. And it was really bad. The more things they bundled together, the better the rating. Certain risky things were assigned. And so it gave people an incentive to continue to bundle things together that they shouldn't have. You always want to check and make sure, can you use the formula? For the geometric series, I should not use the geometric series formula if x is greater than 1 in absolute value. If x equals 1 in absolute value, I should really not even use it. So when I just plug in naively x equals 2, it turns out this can be made rigorous and precise. But you have to have a different notion of length. And the length of a number now, if it's a multiple of p, the higher the power p that divides it, the smaller the number. And so when you have these infinite sums, you don't add them up normally.
Wouldn't that, so if you just let the ratio be 1, wouldn't that mean just the sum of 1 infinite times is completely undefined?
Yes. But I could have 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 equals 1. So do you buy that that equals 1/2?
Sure.
Yeah, half the time, if I stop at an odd term, my sum is 1. If I stop at an even term, my sum is 0. On average, when I truncate, my sum is 1/2. And there are ways to make statements like this precise. If you really like stuff like this, there are, I haven't done this since college, there are series that diverge everywhere where you can get information out of them. Really? Yeah, but you can make this precise and rigorous. So it's a little bit different. But I do agree that superficially it looks a lot alike. The really good economists and the really good physicists have nice intuition as to when you can make things precise and when you can play fast and loose with the mathematics. Wall Street actually sometimes prefers the physicists to the mathematicians because they're more willing to just play with the mathematics. But there's dangers. So we will talk about how to make something like this precise on Monday and actually use this to solve these Diophantine equations. So we will have an introduction to the p-adics. So